Now let's go back to this goal we want to achieve earlier. We just took a digression on the approximation issue of isophysis towards I0. But this is our main goal. We want to extend this I0, which is defined in this intersection, to a left invariant positive linear functional on CCG, so that after achieving this, we can use the Riesz Representation theorem to find the left invariant Radon measure, which will serve as our Haar measure. And the approximation we described in here, will serve as our tool to achieve that goal. So now let's see how to do it specifically. Now for any function f in CCG, where this f is not necessarily positive, we let f be equal to f plus minus f minus, where f plus is defined to be the absolute value of f plus f divided by 2, and f minus is defined to be the absolute value of f minus f divided by 2. Then f plus and f minus are in CCG with restriction to non-negative functions. This is really just a CC plus G union the zero function on G. Now we define I of f as I0 of f plus minus I0 of f minus, with the understanding that I0 of 0 is equal to 0 by convention. Previously, we only defined I0 on CC plus of G, but it doesn't matter just to extend it by 1 point. And that 1 point is just the zero function. Okay, now we have extended the definition of I0 to all of CCG. And keep in mind, if f itself is already a non-negative function, then f is equal to f plus, and therefore I will be equal to I0. So I is really a generalization of I0 to all functions on CCG. Now we are going to verify that I is really a left invariant positive linear functional on CCG. To this end, we need to verify the following couple of things. Let me make a list. First, we need to verify that I is left invariant. And second, we need to verify that I is positive. And third, we need to verify that I commutes with scalar multiplication. And fourth, we need to verify that I preserves the addition. And after the verification of all of these, we can conclude that I is a left invariant positive linear functional on CCG, which will induce a Radon measure on G. by the Riesz Representation theorem. Let's only worry about this later. Let's first worry about how to verify those four things. At this point, I could leave the verification of all those properties for you guys as exercises. Actually, this is more or less done in most textbooks. And textbooks usually do not verify why this random measure is left invariant by G as well. But one of the main features for my YouTube channel is that I always try not to skip details for the convenience of audience. If you think you're pretty strong and motivated, you might want to verify all of this by yourself. But if not, you can continue watching this video. Now we are going to go through all of these one by one. We'll start with the left invariance of I. Let's verify this. First, what do we mean by saying that I is left invariant? We mean this. We mean I of L sub x acting on f is equal to I of f for any x in G and f in CCG. So now let's check this. I of L sub x of f by definition is, let us first break this function down into its positive part minus its negative part. And by definition of I, the extension of I naught to I, this is equal to I naught of the positive part minus I naught of the negative part. But the positive part of the left translation of a function is same as the left translation of the positive part of the function. So you should observe this. Those two guys are equal. And same for the negative part. And now we claim that this I naught has the left invariance property. Namely, this is equal to I naught of f plus minus I naught of f minus, which by our construction is equal to I of f. And now let us verify this equality. We have this equality we have this convergence property. For any f in CC plus G, there exists a sequence phi sub n's such that I sub phi n of f converges to I naught of f. Now, because I sub phi n of f is defined to be f column phi n over f naught column phi n. For any f in CC plus of G, which is left invariant by lemma 1a. Remember, lemma 1 is about some basic properties for the Haar covering numbers with respect to functions. Here, f0, phi(n) are considered fixed, and if you just look at the variable f, I sub phi(n) will be left invariant as a function of f. And by this convergence result, we have I sub phi(n) of f converges to I0 of f as n goes to infinity. So the left invariance of I sub phi(n) will imply the left invariance of I0. Here I know I should use a different notation on the right hand side. Maybe I shouldn't use f, because I have already used f for any general function on CCG, which may be positive or negative. But on the right hand side, the f on the right hand side is always positive. So let me change it to another color to emphasize this. The f here on the right hand side is always a positive function, while the f on the left hand side can be any function in CCG. And now we have verified the first property. Now let's prove that I is positive. This is pretty easy, because for any f in CCG non-negative, which is literally just CC plus of G, union, the singleton consists of just zero function. We have I of f is just equal to I0 of f, because the non-negative part of f, or positive part of f, is just same as f itself in this case. This is also true for the case when f is 0, because remember, by our convention, we have I0 of 0 equal to 0. So, in any case, because I0 of a non-negative function is always non-negative, we have I of a non-negative function is non-negative as well. This proves the positivity of I. So we have verified the second property. And now let's check the third property. Namely, that I commutes with scalars. There are several subcases to consider. If I is 0, then I of 0 is 0. By what we did in here, the convention. So in this case, we have the trivial result, the trivial equality. If lambda is less than 0, then let's look at what we can get from I of lambda f. This guy will be equal to I of the positive part of lambda f minus the negative part of lambda f. And by definition, this is equal to I0 of the positive part minus I0 of the negative part. And this, so let's plug in the definition for the positive part and negative part to see what happens. This will give you absolute value of lambda f plus lambda f divided by 2 minus lambda f minus lambda f divided by 2, which now if you pull out all of the lambdas from the absolute value sign, you will end up getting the first guy is equal to negative lambda times the negative part of f. And the second guy will be negative lambda times the positive part of f. Because lambda is negative, negative lambda is positive, you should expect, as before in the first case, that I0 can commute with negative lambda. So you should expect the last line to be equal to this, which is equal to, if you simplify this, lambda times I of f. This proves that I commutes with lambda when lambda is negative. Now, why is this true? The reason that this is true is the same as the reason you have this part. This is essentially due to this approximation and our lemma 1. But let me still write down the details for our convenience. We have this equality because we have the convergence I sub phi of f plus and f minus respectively to I0 of f plus and f minus respectively. For some sequence phi sub n contained in cc plus of g. As we previously derived. And I sub phi n of some constant times f plus or f minus is equal to this constant times I sub phi n of f plus or f minus for any c greater or equal to 0. This is from our lemma 1. That is why we have this equality. Because each convergent satisfies this communication with constant. So the target of this limit should also satisfy the communication with the constants, non-negative constants. And this finishes this subcase when lambda is less than 0. And if lambda is positive, then the situation might be even simpler, because I of lambda f, which is, if you split this into positive and negative part and use the definition of I through I0, now because lambda is positive now, so the situation is easier to handle than the case when lambda is negative. So in the end, for the same reason, you get this is equal to the lambda times I naught of f plus minus I naught of m minus, which is lambda times I of f. Anyway, in all those three cases, when lambda is 0, negative, or positive, we verified that I commutes with lambda. This finishes our verification of the third property. And now let's look at the fourth property.